Welcome to section 4.2.3. We'll be talking about the Gram-Schmidt process. All right, so in the previous section, we talked about projections, and to get a projection, to get this formula here, one of the things we needed was an orthogonal basis for a subspace. In example 4.2.3, we got away with geometry. We actually constructed an orthogonal basis by using the cross product. For polynomials, for more complicated vector space and inner product space, we don't have the luxury of using the geometry to actually get an orthogonal basis. So in section 4.2.3, we'll be constructing these. So let V be an inner product space, let W be any subspace of V. The Gram-Schmidt process transform a basis of W into an orthogonal basis for W that we can then use in projections onto W. All right, so we'll go from a basis of U to a basis of V's. All right, so start with a basis for W. To get an orthogonal basis for W, the first element of that orthogonal basis, pretty simple, just take V. All right, so U1 is V1. Then V1 is U1. We cannot take V2 to be U2 because we don't know that U2 and U1 are orthogonal. So we need to make sure it is. So what we'll do is we'll take away the projection onto the ones that we already have used. So that's going to make sure, so this is take away the projection onto the span of this, onto the line of this. And so this one is the orthogonal component. And so that's going to make sure that V2 and V1 is are orthogonal. And we're going to do the same thing. When we use U3, it might not be orthogonal to U1, so we take away the part that's along V1. So U3, V1, 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 and we take away the part that's along V2. All right, so what's nice is the V1 and V2 are already orthogonal, so I have my basis to do projection on their span, and so on. We always, actually, let me put it that way. That's going to be easier to write here. So I'm going to take UK, V1, 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 UK, VK minus 1, VK minus 1, VK minus 1, VK minus 1. All right, so you take away everything that's along V1 and VK. So at each step, we're using projections. In fact, if we take WJ to be the span up to J, then VJ is UJ, and then you take away the part that's, oh, sorry, that should be, actually, it's the same thing, but let's write it this way. It's going to be a bit clearer. And so projection W onto WJ minus 1. And so it's really the part of UJ that's perpendicular to the vectors you're already using. All right, so let's apply this in R3, right? We've already shown how to use geometry to do these problems, but I'm asked to apply the Gram-Schmidt process to get an orthogonal basis out of this. All right, so let's call these U1, U2, U3. They're vectors, so I'm going to put, oh, it just jumped. I'm going to put arrows on them. All right, so we're told to take V1 to be U1. And so that means I'm going to take it to be the vector 1, 1, 1. I'm going to take V2, I'm going to take U2, and I'm going to subtract the dot product. Let me write it as an inner product. That way it's going to generalize more easily. Of U2 with the vectors I've already constructed. So in this case, just V1. And I'm going to multiply that by V1. All right, so that's U2 is 0, 1, 1. I'm going to subtract the dot product, so that's of these two vectors. So that's 1 times 1 plus 1 times 1. And I'm going to divide by v1 dot v1. That's 1 plus 1 plus 1, so that's 3. And I'm going to multiply this by 1, 1, 1. So this here is 2/3. And so I'm going to take minus 2/3, 1/3, 1/3. All right, and you do the same thing with V3. V3 is going to be U3 minus, you take U3, V1, 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 plus U3, V2, 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 V2. All right, so U3 is 0, 0, 1. U3 dot, well, V1 is here, but it's also here, so that was just 1. Length of V1 we saw is 3. And then, all right, U3, sorry, dot V2 is 1/3. The length of V2 is 4/9 plus 1/9 plus 1/9, that's 6/9, times minus 2/3, 1/3, 1/3. All right, so this here is just 1/2. And so what I get is 0 minus 1/3 minus 1/3. So I get, wait, 0 minus 1/3 plus 1/3. I get 0. Then I get 0 minus 1/3 plus plus a 6. So I get minus a half. And then I get 1 minus 1/3 plus a 6th again. And so I get 0 minus a half plus a half. Sorry, I'm a bit low on space. I'll give you more on your notes, but let's give the answer here. So my orthogonal basis is minus 2/3, 1/3, 1/3, and 0 minus a half,